This is a super subtle point, but it clearly says that comparing clocks between two moving observers is a tricky business. You need to take into account both the time each experiences and the location at which the comparison is going on. Further, they both agree that the remote person's clock is slower. You probably need to think long and hard about this and maybe even rerun this video to get your head around this idea.
That's a funny little argument I gave there, isn't it? For those of you who are at least a little perceptive, you must have already noticed that the notion of remoteness he used here is completely relative. So if the agreement relies upon something they can disagree, the agreement itself can be disagreed, so this argument is completely flawed. It seems like even denying relativity in itself is a valid form of defending it. Dr. Don Lincoln makes a point throughout the entire video that it's possible for two inertial observers to agree about who is older, avoiding the twin paradox. My biggest focus in this video will be the calculations, since I know pretty well that most people didn't get convinced by his nonsense arguments, but by not understanding the calculations to a very deep level. My response is going to be very simple, and it's going to consist in 2 points. My first point is that if the symmetry is not broken, there cannot be an agreement between the subjects on age, and I'm going to demonstrate that. And my second argument is that the symmetry is not broken, which is also going to be demonstrated. Before diving into the equations, I'm going to make a conceptual sketch of my argument. Following Einstein's first postulate, the principle of relativity, we can state clearly that the laws of special relativity should work precisely the same for every inertial body, regardless of their relative position. The symmetric property of the Lorentz transformations with regards to two inertial bodies appears to be a direct implication of this principle, since when changing from one frame of reference to another, the perceived velocity of the other subject should have the same magnitude and opposite direction. Considering that only the magnitude of the velocity is relevant for determining effects such as time dilation and length contraction, and not its sign, there is no reason to expect the transformations to give different results given the specified conditions. As a very brief introduction of the Lorentz transformations, I'm going to say what they are and what they do. Why would you need them? The Lorentz transformations as being showed here allows to pick the spacetime coordinates of an event and know what are the spacetime coordinates of the same event in another frame of reference. The most basic feature of the Lorentz transformations is that they preserve the speed of light in every frame of reference. Just as a little side note, the Lorentz transformations have some restrictions, which are made to simplify the formula. The restrictions are that both frames of reference have their origins meeting when time and space is equal to 0. It's more common to draw the transformations on top of one another in a single plane for this very reason. It makes formulas simpler. Just before the calculations, I'm going to introduce a new notation. For time and position, the first subscript letter is going to represent the event to which it belongs, and the second is going to represent the frame of reference where it's being measured. TEA is going to be the time of event E in the frame of reference A. XEA is going to be the position of event E in the frame of reference A, and VAB is going to be the velocity of A from B's frame of reference. Instead of calling the subjects observer 1 and observer 2 like he called, we are going to call them Alice and Bob, respectively, and abbreviate as A and B. I am fully aware that this notation is far from standard, but I think this is the best way to express the equations. Just so nobody thinks I'm trying to trick them by changing the meaning of the equation, I recommend that you check out a book by Wolfgang Rindler called Introduction to Special Relativity, and there you can see that the notation he uses, although different, means the same thing. I'm going to start by changing the layout a little bit. All the time we are going to keep track of both frames of reference, and we are going to analyze the situation by applying the correct transformations in both frames. Just like previously, they are going to measure time by using their clocks. Alice is going to see Bob moving to the left at velocity -v. Similarly, Bob can claim he's not moving and that Alice is moving to the right at velocity v. Now that we have understood the situation, we can now describe it by using the equations. The first set of equations, labeled equations for Alice, are the equations used in Dr. Don Lincoln's original video. I believe I have already explained well what the variables mean, but the subscript E and the subscript F both mean two events which are not necessarily the same. Since we have already agreed that VBA, that is, the velocity of Bob as measured by Alice, is -v, we can already make the first substitution. Similarly, we have agreed that VAB is V, so we can also make a substitution for Bob. We can also notice that gamma AB equals gamma BA, since 1 over square root of 1 minus v squared over c squared equals 1 over square root of 1 minus negative v squared over c squared. Let's call it gamma for simplification. For the calculations, we are going to consider event E as stuck to Alice and F as stuck to Bob. Just as an example, we can think of event E as something like Alice smiling. Now we can already make the substitutions. We are going to consider XEA as 0, since we have agreed that event E is going to be at the same position as Alice. We are also going to consider XFB as 0, since we have already agreed that event F happens at the same position as Bob. We can see that the equations simplify a lot, but there is still some work to be done. Next, we are going to consider that XFA equals minus V times TFA. Similarly, we can consider XEB as V times TEB. Next, we can factor out TFA and TEB in both of the equations. Notice that the expression that appears in both of them is 1 over gamma squared, so we can make the substitution. Simplifying the equations even further, we can clearly see that the expressions that appear on top are precisely the same as those that appear in Dr. Lincoln's video.
Let's first find out what observer 2 thinks the time is at observer 1's location. We just put in the value seen by observer 1. In doing so, we find that t sub 2 equals gamma t sub 1. That's just the normal time dilation equation. Now let's do the same thing for how. That means that this equation can be written as t sub 2 equals gamma divided by gamma squared times t sub 1. And finally, we get t sub 2 equals t sub 1 divided by gamma. That's divided, not multiplied by. That's exactly the opposite thing we saw when we looked at what was happening at observer 1's location.
His mistake, however, was to think that the second equation for Alice helps his point, when it does exactly the opposite. This can be made more clear by multiplying both sides by gamma. Now that we have properly organized the equations, it's time for the great revelation. Let E be an arbitrary tick of Alice's clock, and F be an arbitrary tick of Bob's clock. If that is still too hard to understand, we can pretty well work with numbers. Let's assume gamma equals 2 at v equals 86.6% the speed of light. We're going to call event E as Alice's clock hits 10 hours and label it as 10 HA, and event F is going to be called Bob's clock hits 10 hours and is going to be labeled as 10 HB. Now we can change the information in equations for Alice and see the final result. We can see here clearly that it takes twice as long for Bob to see Alice's clock hitting 10 hours than it takes to Alice. Similarly, we can see here that it takes twice as long for Alice to see Bob's clock hit 10 hours as it takes for Bob. Now it's time to return to my response and analyze my two major points. We have seen that an arbitrary symmetrical situation without loss of generality has been assumed, and this implied in the disagreement about who's older. The situation chosen in Fermilab's video falls into the group of situations that can be described by the present formulation, and it is possible to describe them as symmetrical while keeping it contained within the principles of special relativity. Now this video is already complete. If you wanna leave, you can leave already, but if you're going to stay until the end, bear in mind that the following content is purely conjecture, and I made those conjectures in very little time, so these conjectures can pretty well be wrong. Now we can follow to some hypothetical questions. Is relativity broken? My answer is, not necessarily. The twin paradox is not and does not directly imply in a logical contradiction. It is therefore logically possible, at least in first analysis. Can this weird effect described be verified empirically? Well, I don't think so. Let's suppose Alice uses her very advanced smartphone to take pictures of herself and send to Bob. She sees Bob as young and sees herself as old. When she sends a picture of herself, does Bob see her picture as being different from what he sees if he looks at her with a telescope? Well, probably not. The causal chain of the picture that reaches Bob is related to his own world line. What I mean by this is that Alice was only able to take this picture because photons were reflected by her face into the camera. But if Bob sees her face as being young, then he should perceive the reflection accordingly, and as a consequence the picture too. So what he sees in the telescope should agree with what he sees in the picture. Of course, the situation is also symmetric, and the same happens to Alice. In addition, taking a picture is an arbitrary example, and could be replaced by any other action that leads to the same end, as long as it follows a causal chain determined by Ohm's world line. Considering this notion of causal chain, Alice will agree with Bob in his own world line about everything, but will disagree with herself and with Bob in her own world line, rendering a weird picture of reality. The most impactful consequence of this interpretation I am presenting is that, if correct, It would mean that two observers won't just disagree about the quantitative extrinsic properties of an event, but they can pretty well disagree about the whole factuality of an event. In other words, a multiverse is a direct implication of special relativity if all inertial frames of reference are truly equivalent. This has been Analytic. Thank you all for watching.